Okay, guys, we need to talk about complex numbers. So let's start out looking at an example of where you might see a complex number. They tend to come up when you're solving quadratics. It's usually a special case where this happens at, so I think this one should work. So this problem here won't factor based on the signs, but we could find the solutions. We could find the x-intercepts by using the quadratic formula. X equals minus b. Since b in this case is negative, let's go over here and write what a and b and c are. So your formula is minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So we're going to try to simplify this down. So we have 3 plus or minus the square root. Well, negative 3 squared would be 9. And 4 times 4 times 1 would be 16. All over 2. So x would be 3 plus or minus the square root of negative 7 over 2. And usually at this step you would just stop. You'd be like, oh, well, I can't take the square root of a negative number, so I'm done. Well, now you kind of can. So a complex number is one where you're taking the square root of a negative. And what we're going to do is we're going to say that the square root of negative 1, every time we see that in a problem, we're going to replace it with I. In other words, we're going to say that the square root of negative 1 is an imaginary number. We're going to call it I. So here, we really have 3 plus or minus the square root of 7 times negative 1 over 2. And I'm going to split that out. And that square root of negative 1 part, I'm going to call that I and say that x equals 3 plus or minus I times the square root of 7 over 2. So what does this mean in terms of finding solutions to a quadratic? Well, what it means is that you're going to have two complex solutions. In other words, if you were to graph this, this parabola, we can see that it's going to open upward. Since I know that I have two complex solutions, what that means is it's not actually going to cross the x-axis at real numbers. It's going to cross not at all, really. So it'll look maybe something like this, where your vertex is above the x-axis. So it's not going to cross down here. You won't get real solutions. You have 0 real solutions, but you have two that are complex. So complex numbers have a couple really cool patterns that come up with them. And there's really about 4 different types of problems that you'll see. So one of them that we can do is we can look at powers of complex numbers. We can divide them. We can multiply them. And we can take the absolute value of them. So I'm going to do a couple examples of each of these types of problems, things that we can do with complex, and then we'll go from there. So what I want to start off with is the powers of complex numbers. So we know that I, we've said already, that's the square root of negative 1. Okay, so no big deal there. What happens if you take I and you square it? In other words, if you take the square root of negative 1 and you square that, well, a square root and a square, those are inverse operations of one another, so they cancel each other out. You're just going to get negative 1 there. So if I is the square root of negative 1, then I squared would be negative 1. What about if you take I to the third power? Well, that's the same thing, using exponent rules, as I squared times I. And we just said that I squared was negative 1. So if I multiply negative 1 by I, I'm just going to get negative I. Okay. What about if you have I to the fourth power? Well, again, using exponent rules, that would be the same thing as I squared times I squared, which is like -1 times -1, which would be +1. And then something neat happens when you go beyond that. Well, I to the 5th would just be I to the 4th times I, and I to the 4th is 1, so you just get I again. And I to the 6th, again, that'd be I to the 4th times I squared, so you'd get -1 again, because that's what I squared is, and I to the 4th is +1. I to the 7th would be I to the 4th times I to the 3rd. Again, if this is 1, that's just I to the 3rd, which again is -I. And this pattern tends to repeat. So based on the power, if 4 goes into it, and then you look at the remainder, you can figure out which one it is. So for example, if I had the problem I to the 12th, and I want to figure out what that is, well, I can look and see how many times does 4 go into 12. It goes in there 3 times. And I get 0 as my remainder. That would correspond to I to the 4th. And I would know that I to the 12th is equal to 1. Okay, so this is remainder of 1. This would be remainder of 2, remainder of 3, remainder of 0. Okay, what if we had I to the 43rd power? Well, again, 4 would go into 43 one time, and then so it goes into 4 once, and then it goes into 3 0 times, and we get a remainder of 3. Remainder of 3 corresponds with -I. And let's do one more. I to the 781. Okay, again, you're just trying to see how many times does 4 go into that. Well, 4 goes into 7 one time. 1 times 4 is 4, and then subtraction, you get 3. Bring down the next number. 4 would go into 38 9 times. And 4 would go into 21 5 times. And 1 left over. So since you got remainder 1, that would correspond to just plain old I. Okay, so again, the patterns repeat every fourth power. So 5 is the same thing as a 1, 6 is the same thing as a 2, 7 would be the same thing as I to the 3rd, so on and so forth. So that's powers of complex. Let's look at how to multiply complex numbers. Okay. So we may start off with something like 3 plus I times I. We'll start off with something really simple. So here we're just going to distribute. 3 times I would be 3I. And I times I would be I squared. But then recall that I squared is the same thing as -1. So you'd end up with 3I minus 1 as your final answer. Okay. What if we have one like this? Well, here we're going to have to distribute twice. So let's start out with 2 times 5. That would be 10. 2 times -I would be -2I. And distribute the second term. I times 5 be 5I, and I times -I be -I squared. So we can combine some stuff here. We know that -2I plus 5I would be 3I. And we've said before that I squared, that's the same thing as -1. So if I'm subtracting -1, that's kind of like adding 1. So 10 plus 1 would be 11. Okay, so that's multiplying. You really won't have to do too much beyond that, so it's pretty easy. Some people will fuss at you if you don't write your answer in standard form. So usually complex numbers are written in the form A plus BI. In other words, the part with the I comes second. So here we might want to rewrite this as -1 plus 3i. And here we can rewrite this as 11 plus 3i. Not going to make a huge difference, but yeah, you know. Oh, one other thing that we can talk about real quick while we have these two examples is the conjugate. Just reviewing that. Remember that the conjugate has the same numbers in it but different signs. So for example, if I was going to find the conjugate of 1 plus 3i, that would be, or sorry, -1 plus 3i, that would be -1 minus 3i. So we're still taking the -1 and the 3i, we're just changing the number that's between them, or the sign that's between them. So here, the conjugate of 11 plus 3i would be 11 minus 3i. Okay? So that's multiplying and the conjugate as well. Next would be dividing. How do we divide complex numbers? So let's start off with an easy one, 3 over 7i. So the problem with this, recall that I represents the square root of -1. And you may recall that you're not supposed to put a square root in the denominator of a fraction. So to get rid of it, you would just need to multiply the top and bottom by the square root of -1. So here, if we're looking at this in terms of I, you're really just multiplying the top and bottom by I. In other words, I divided by I is 1, so you can multiply something by 1 and not change the value of it. But what happens when we do this is we're going to get 3i on top and 7i squared on the bottom. And then recall that I squared is the same thing as -1. So your final answer would be -3i over 7. Okay? Pretty simple. Some examples will get more complicated than that, however. You may see something that looks like this. So we have a binomial in the bottom, and one of them is the square root. So remember that to get rid of this, you're going to multiply using the conjugate as your form of 1. So 4 plus I over itself, that should be 1. We're really multiplying by 1, so we're not changing the value. But when we multiply by the conjugate, something special happens on the bottom, and it gets rid of all of those i's. So on top, we'll distribute. 3 times 4 would be 12. 3 times I would be 3i. I and 4 make 4i. And I make I squared. On the bottom, again, you'll distribute. 4 times 4 is 16. 4 times I is 4i. Negative I and 4 is negative 4i. Negative I and I is negative I squared. And then we're going to try to simplify this down. So, again, remember that all those I squareds, those were -1s. So, 3i and 4i would be 7i. 12 minus 1 would be 11. On the bottom, 16 minus a -1 would be 16 plus 1, which is 17. Plus 4i and minus 4i cancel out. So we end up with 11 plus 7i over 17. So there's no more i's in the denominator, so that's where you would stop. Okay, so use the conjugate to help you simplify things like this. And then the last thing that, the last kind of operation thing that you can do with absolute values, or with complex numbers, is absolute value. So what I mean by that is you'll have maybe 3 plus I in absolute value. So there's two ways to think about this. There's the shortcut method, so once you learn the trick, you can just kind of jump into that. Before you get there, we want to talk about how do we graph a complex number like this. So the way you're going to do it is the real number part of this will be the x-axis, and the imaginary part of this, we're going to put that on the y-axis. So you can see that our real number here is 3, so we're going to go over 3. And then our imaginary part is plus 1i, so we're going to go up 1. So this would be the point at 3 plus I. So absolute value, what we're measuring there is the distance that is from 0. How far is that away from the origin? So in other words, how far is that? So notice here that if I just drop this line down, what I've got is I've got a right triangle. Notice that the height of my right triangle is 1. The length here is 3. And I can use the Pythagorean theorem to find how far is this point away from the origin, to find this distance. So recall that x squared would equal a squared plus b squared. So x would be the square root of a squared plus b squared. So we get the square root of 10. So I skipped a couple of steps there. So the shortcut here, really, you're just taking the square root of the first number here squared plus the coefficient on the I squared. So this is like a 1i. You're just squaring the 1. Don't worry about the I here. That's not part of your answer. So here, this would be the square root of 10. Okay, I'm going to do a couple more of the absolute values so I can kind of clarify some things. So let's look at the absolute value of 7i minus 3. So again, you can think about this as graphing. Okay, as always, someone always interrupts my my videos. So coming back to this problem again, we're gonna go ahead and graph this. So remember that the imaginary part of your complex number is going to go on the y-axis, 4, 5, 6, 7, and the real part is going to go on the x-axis. So if it's negative, we're going to go to the left. So we have a point right there. This is the point at negative 3, 7i, or negative 3 plus 7i if you want to write it that way. So again, you're going to make a triangle out of this. We want to find how long is the hypotenuse. So we know that this length here is 3. This one is 7. So we have a triangle with sides of 3 and 7. We want to find the hypotenuse. So recall that a squared plus b squared equals c squared. And if you take the square root of both sides, you get the square root of 9 plus 49, which would be 58. And then, so we know that the absolute value now of 7i minus 3 would be the square root of 58. Anything else that we want to do is just check to make sure that this can't reduce. So 58, for example, would be 2 times 29. And I'm pretty sure that 29 is a prime number, so yeah, it doesn't look like this is going to reduce down. So your final answer would be the square root of 58. That'd be where you'd stop. If you just have the absolute value of just the complex part, the absolute value of 3i, well, if you go up 3 on the complex and you try to figure out how far away is this from the origin, well, you can see pretty easily that it's just 3 units. So if you recall that you can always graph a complex number, remember that the real number part of it goes on the x-axis, that the imaginary part goes on the y-axis, up and down, and then find how far away is that point from the origin. That's what this is measuring. Absolute value measures distance from 0. And really, that's about it that you're going to see with complex numbers. Absolute value, multiply, divide, and look at powers of them. And really, I guess that's about it. So if you have any questions, feel free to leave a comment below. Otherwise, good luck with your math adventures.